Morning class. Let us quickly revise what we have understood in yesterday's class. In yesterday's class, we were deriving three important physical quantities vis-a-vis to the unit cell, namely the coordination number of the unit cell, its atomic packing fraction, and the correlation between the radius of the atom and the corresponding lattice parameter. So yesterday we have understood this quantity for the simple cubic structure. You know, the simple cubic structure is the one where only corners are being occupied by the lattice point and every corner contributes 1/8. So effective number of atoms within the unit cell is coming out to be 1 atom per unit cell. And if you want to find out the number of nearest neighbor which a given atom has, you have to follow the diagram which is shown on the lower right hand corner, where you can see that one atom is surrounded by its 6 equidistant neighbor. For example, if you focus on this blue color atom, then it is at equidistant from one on the left, one on the right, one on the back, one on the front, one on the top, and one at the bottom. So likewise, this is true for every other atom. You have 6 nearest neighbor corresponding to every atom, and that is why the coordination number for the simple cubic structure was 6. Then we define another important parameter which we will frequently refer vis-a-vis to the unit cell. It was called APF, or atomic packing fraction. It represents the fraction of the total volume that is occupied by the atom. So it is being defined as the ratio of volume of atoms within the unit cell to the total volume of the unit cell. Interestingly, the APF only depends on the crystal structure and it is independent of the radius of the atom or the lattice parameter of the structure. So it will be a constant number and varies only if you alter the crystal system. So we will keep deriving the APF number for important unit cell types. Yesterday we have also understood the coordination number and the APF for the face-centered cubic structure. Amongst the cubic class, FCC is very, very important. Many important metals like aluminum, silver, gold, lead crystallizes themselves in this unit cell category. So we know how the FCC structure looks like. It is the unit cell where atom occupies the corner side as well as center of each of the 6 faces of the cube. The side distance are A, which is the lattice parameter of the unit cell. And if I look along the face diagonal, what I can see is there are 2 corner atoms on the face diagonal and 1 central atom of the face. Now, I have 2 different representation, the representation on the left and the representation on the right. The representation on the right is called the closest packing approximation, where we assume that every atom is in physical contact with each other. That means boundaries of the atom touching each other. So if you go through that assumption, then you can define the total length of the face diagonal, which is shown in the right hand corner image, as R plus 2r plus r, that makes the total length to be equal to 4r. And you can use the Pythagoras here. So the square of the sides, which is a square plus a square, should be equal to 4r whole square. So if I rewrite this, it comes out to be a to be equal to 2 under root 2r. This expression you have to remember for an FCC structure where the relationship between a and r is a equal to 2 under root 2r. And then we have computed the total number of atoms making the unit cell. So we have two different contributions coming from two different atom positions. One is the corner positions where every atom contributes 1/8, like the simple cubic. So you have 8 such atoms making the corner and each contributing 1/8. So 1/8 into 8 gives you one effective atom in the unit cell. And then we have 6 faces, each occupied by one face atom. So 6 into the contribution of face atom is half because it is being shared between two neighboring unit cells. So 6 into half makes 3 and 1/8 into 8 makes 1. Effective atom comes out to be 4 atoms per unit cell. Then in the last class, we have also understood the APF for an FCC unit cell. If you go back to the definition of APF, it's a ratio of volume of atoms within the unit cell to the total volume of the unit cell. Since it's a cube, so total volume of the unit cell will be V equal to A cube. And if you substitute for A in terms of R, which is 2 under root 2R, you end up to volume of the unit cell as 16 under root 2R cube. Now we can also compute the volume of the atoms. We know there are 4 effective number of atoms. So my volume of the atoms will be 4 times the volume of one atom, which is 4 by 3 pi r cube. So now if I substitute these two volumes into the expression for APF, that is APF is equal to the ratio of volume of atoms to the volume of unit cell. So if I substitute these numbers and simplify it, it comes out to be 0.74, which is independent of the radius of the atom as well as the lattice parameter of the unit cell. So as long as your unit cell type is FCC, your APF is always constant and fixed at 0.74. Remember this number 0.74. I will get back to this number at a later stage. So for a time being, you have to remember that out of the entire space available for an atom to sit in an FCC unit cell, 74% of the total space is being occupied by the atom. And you will see that this is the highest possible packing that atoms can achieve in a crystalline form. So the highest packing efficiency is 0.74. Then let's talk about the coordination number of an FCC unit cell. Now, first thing that you should look at is which is the closest possible distance in a FCC unit cell. We have two possible directions in which one can look at. One is along the face diagonal and another is along the edge. So we know the distance between these points are different, and the smallest possible difference between the distances between the atoms will be along its phase diagonal. If I go back to this diagram, you can see this distance is smaller as compared to this distance. So this will be, that is, center of the face atom to one of the corner atom is the smallest possible distance. So how many such closest neighbor you have in an FCC unit cell? If you want to count that, you have to focus on this right hand side image and focused on the atom which is on the right hand face of the unit cell. This atom has 4 nearest neighbor within its face. So if I look this particular face, it has 4 corners, 1, 2, 3, 4. So you can easily visualize 4 nearest neighbor belonging to this particular atom. Now, if I look on the back face of this unit cell, then I can find one more central atom which is also at the same distance. Likewise, I find another atom on the front face, another atom on the top face, and another atom on the bottom face. So, how many total? 4 within the plane, another 4 on the back side of it, and if I look on the front of this, then there will be another unit cell whose faces, the 4 faces, also have one central atom, and all of them are at equidistance. How much distance is that one? It is 2 under root 2 r by 2 is the distance, because your total distance was under root 2a, and that is the total diagonal length. You have to divide it by 2. That makes the closest possible distance in an FCC unit cell. So if I now count with reference to this face atom, how many nearest neighbor I have? 4 within its plane, 4 on the back side, and 4 on the front side. It makes 4 plus 4 plus 4 to be equal to 12. So coordination number of an FCC unit cell is equal to 12. I hope everybody got this, why the coordination number of an FCC is 12. Okay, now let's move to the second important brevis lattice type, which is body centered cubic or BCC. Many important metals like chromium, iron, molybdenum, titanium, tantalum all crystallizes into a body centered cubic unit cell type. You can visualize a body centered cubic unit cell as the lattice points making the corner sides as well as center of the cube. And with closest possible approximation, you can visualize it to be like this, where you have corners occupying the unit cell, and then there is one central atom. Remember, when we use the closest approximation, you have to remember that every atom touches physically with its neighbor. So your central atom is in physical contact with all neighboring 8 corner atoms. So both figures are correct. The central one, and the one which is left one. For all mathematical purposes, we will follow the leftmost image, and for the sake of representation, for better clarity, we use the central image. So if I replicate this unit cell, I end up into a solid which in 3D looks something like this, which is marked in the right handmost image. When you can clearly see a unit cell can be shown on the 3D arrangement of periodic assay of atoms. Now what we will do is, we will find out the effective number of atoms in this unit cell, its coordination number and its APF. So let's first find out the effective number of atoms making a BCC unit cell. Here we have two different contributions, one coming from the corner sides and another one is coming from the center of the cube. So like always, every corner contributes only 1/8 and you have 8 such corner atoms. So 1/8 into 8 makes effective contribution to be equal to 1. While the central atom is completely within the unit cell, so it contributes 100% to the unit cell. So your effective contribution is now 1/8 into 8 plus 1 into 1, which makes 2 atoms per unit cell. So for BCC, you have 2 atoms making the unit cell. Compare it with the FCC, we have almost double than the BCC. For FCC, we have 4 atoms per unit cell, while in BCC, we only have 2 atoms per unit cell. Now, we want to derive the APF for a BCC unit cell. Remember, whenever you want to derive APF for any unit cell type, the first thing that you should do is you should identify the correlation between the radius of the atom and the corresponding lattice parameter. Now first focused on the left hand side image. We have one BCC unit cell. Now whenever you want to derive APF, you should look along the direction where you have highest number of atoms sitting. In previous case, while we were discussing the FCC unit cell, we had look along the face diagonal because an atom was sitting on the face. In case of BCC, we have atom sitting in the center, so we should look along the body diagonal. So if I now look along the edge, the vertical edge, which is height, it is equal to A, the lattice parameter. The length of the body diagonal, I can define in terms of the radius R as, that you can easily understood from the right hand image. I have only fraction of the atom of the corner side whose length is equal to R, then an entire middle atom whose total length will be 2R, and then the opposite corner atom whose radius is equal to R. So my total length of the body diagonal is 4R. And if now I come back to the left hand side image and focus at the face diagonal on the top face, we know that the sides are A and A each. So your face diagonal length is under root 2A. So now if I focus on this particular triangle, focus on the red mark, the laser mark, which I am pointing at. I am starting from this lower corner atom, moves top, then along the face diagonal, and then come back along the body diagonal. So it's a right angle triangle, and I can use the Pythagoras there to find out the correlationship between A and R. So I am doing this. The square of this side is A square plus square of the face diagonal is under root 2A whole square. should be equal to square of 4r. So if you simplify this, I find out my A to be equal to 4r by under root 3. So this is the relationship between A and R for a BCC unit cell. You have to remember this again while solving the numerical problems. Now we are defining the APF, which is the ratio of volume of the atoms to the volume of the unit cell. Your volume of the unit cell will still be the same because it's the cube, and volume of the unit cell is A cube. And if I substitute for A to be equal to 4r by under root 3, it comes out to be 64r cube upon 3 under root 3. This makes the volume of the unit cell. And now I need volume of the atoms. So how many atoms are there in a BCC unit cell? The effective number was 2. So my total volume of the atoms is 2 times the volume of an individual atom, which is 4 by 3 pi r cube. So if I substitute this and this here and simplify this, it comes out to be 0.68. That means the packing efficiency or atomic packing fraction of BCC is lower than FCC. For FCC, it was 0.74, while for BCC, it is 0.68. Another important thing is the APF for BCC is also independent of the radius of the atom or the lattice parameter of the unit cell. So whether I take iron or molybdenum, its packing efficiency will be same because both crystallizes themselves into the BCC unit cell. You remember while beginning this course, I said we will not going to study individual materials, rather than we will going to study materials in different classes because they all possesses an identical properties. And this is replicated here. Whether I talk about iron or molybdenum doesn't matter as long as I describe a BCC unit cell, because the packing efficiency equal to 0.68 is true irrespective whether a particular atom X or another particular atom Y making that particular unit cell. I hope this is clear. Now coming to the third important parameter belonging to the BCC unit cell is the atomic packing fraction, or the coordination number, not atomic packing fraction. Atomic packing fraction we have already described. So coordination number for a BCC unit cell can be very easily visualized because you can see the direction in which one should look at. You should look at along the body diagonal. So we know that you have 4 possible body diagonals passing through the central atoms. And if I measure the length of the body diagonal vis-a-vis to the center of the body atom, then they are all equidistant. What is my point? My point is, if I measure the distance of center of red atom to the first corner atom or second corner atom or third or fourth or fifth, sixth, seven or eight, they are all at the same distance. So the coordination number for the BCC unit cell is equal to 8. I hope this is very clear to you now. How the two unit cell types, namely the BCC and FCC, differs from each other. Here is the summary. For BCC, we have the correlation between A and R as A equal to 4R by under root 3. Two unit cells, 2 atoms per unit cell makes the BCC unit cell. Its coordination number is 8 and its atomic packing fraction is 0.68. While for FCC, the correlationship between A and R is A is equal to 2 under root 2 R. 4 atoms makes the unit cell. The coordination number is 12 and its APF is 0.74. So you should always remember while solving a numerical problem, whenever we refer a BCC structure, you should look along the body diagonal, and whenever we refer an FCC unit cell, you should look along the face diagonal. If you proceed like this, your derivation will always be correct. If you have any doubts up to this point, you can raise them through chat. I will be happy to answer that, because then we will move to a more complicated structure of hexagon. So if you have any questions or queries, please raise them. I will wait for a minute and then we will move to the hexagonal structure. Okay, there is a query for coordination number and APF for an end-centered cubic structure. We will come to the end-centered cubic structure at a later stage. So that was the pending question yesterday also. We'll get back to the end-centered cubic structure at a later stage. But it's very easy because you can say half of an FCC structure. So where you should look is only on the two opposite faces. So you can compute the effective number of atoms and the coordination number while looking at the center of one of the faces. So I will come back to the end-centered cubic structure maybe tomorrow. Okay, I guess couple of students could not get themselves clear on the coordination number for an FCC unit cell. So I'm going back to that particular slide where we have a discussion on coordination number for the FCC unit cell. Okay, focus on the atom where my cursor is there. Whatever I talk, I am talking vis-a-vis to this particular atom. Now, if I look along the face diagonals on the right hand side plane where my cursor is there at present, I can see 4 corner atoms which are all equal distance vis-a-vis to the central face atom. I guess it is easy to visualize for everybody. So 4 of them are within the plane. The remaining 8 are little bit difficult to visualize. Remember the definition. What is the definition? We define coordination number as the nearest neighbor, and nearest neighbor means all the neighbors has to be at equal distance. So what I suggest you to calculate is the distance between the right hand face centered atom and the face centered atom on the top of the unit cell where my cursor is there. So what I am asking you to compute, I am asking you to compute a particular distance which is this one. I am asking you to compute this particular distance, which is now I marked as a blue color arrow. So if you compute this distance and if you compute this particular distance, it is both coming out to be same. You can do yourself numerically, use a simple geometry. Why? Because you know this is also the face diagonal. This is also the face diagonal. So you know this is half of the face diagonal. Likewise, this is also the half of the face diagonal. So you can compute this distance and it will precisely come out to be the same number, right? So you can do it mathematically by yourself. So now if I start counting, if this distance and this distance is same, then this is also the face and this is also the face. So if I compute this, it will also be same. Likewise, if I compute this, it will also be the same. And likewise, if I compute this, it will also be the same. That means vis-a-vis to this central face atom, I can find 4 closest distance with 4 surrounding central faces. Which 4 central faces? Top, bottom, front and back. These are the 4 ones. And now if I move 1 unit cell ahead, then I can find similar situation. I can find similar situation in the front side. This is the front face central atom. This is the back face central atom. This is the top and this is the bottom. So 4 on the back, 4 on the front and remaining 4 within the plane. 4 plus 4 plus 4 makes its coordination number to be equal to 12. Okay, I guess now it is clear to everyone. So if there is any further query, please raise it up to this particular discussion, because now the things becomes little bit more complex when we move to the hexagonal structure. Okay, I guess there are no further doubts up to this particular point of discussion. So we are moving to the next topic, which is the closed pack structures, or in general, the hexagonal structures. So for a while, I am stopping the share and I'm moving to another PPT.